All right, I'm going to start with esters. Esters are a nice place to start. They're not overly reactive, but they do react with nucleophiles. And so we're going to look at two things. We're going to look at adding organometallics like Grignard reagents to esters and see what happens. And then we're also going to look at adding lithium aluminum hydride, so H minus, adding to esters and that kind of thing, and see how that differs from the ketone and aldehyde reactions that we learned in a previous lifetime. Okay, so let's start with lithium aluminum hydride and esters. Okay, so let's take an ester. Let's use, what ester should we use? Let's use benzyl benzoate. I haven't used that one yet. All right, so we have our ester here. We got a carbonyl with an oxygen attached to it, right? Ester over here. We've got lithium aluminum hydride. You guys already know. I'm going to also say that this is a present in excess. It's usually a safe bet with lithium aluminum hydride. You guys know what to do with lithium aluminum hydride. That is just a source of H minus. So lithium aluminum hydride is H minus. We know that H minus does not need a carbocation to attack. It can just attack a carbonyl. It attacks the carbonyl carbon. It pushes an electron, pair of electrons up onto the oxygen and makes a lone pair. And we end up with this thing. And now in previous chapters, we would have stopped here, right? We would have said, oh, we've added the H minus. Everything's good, right? There's nothing left to do. We should add some H plus and we'll be done. The thing here is that we have an actual leaving group here, right? Oxygen is not a great leaving group, but in this case, it's good enough that we can have this group leave. And as it leaves, we'll use this extra lone pair to, again, if this just left, we'd create a carbocation here, but instead, we've got a negative charge up here, so we might as well share those electrons back down here, and we get an aldehyde. So, plus whatever our leaving group is. Right? This is a negatively charged oxygen with the rest of the group attached to it. So this leaving group isn't terribly interesting. What is interesting is that we have an aldehyde, and because I said we have excess lithium aluminum hydride around, we already know what happens to aldehydes when lithium aluminum hydride is around. We're going to add to that carbonyl again, and we're going to end up adding 2 equivalents of H minus to this. We're going to get a primary alcohol out of this reaction. So again, notice what happens is we add H minus and then we get to our intermediate, and then in this case, because we have a leaving group, this oxygen leaving group, we can reform the carbonyl and kick that leaving group out. And then once we reform the carbonyl, lithium aluminum hydride is hanging around and attacks that carbonyl and gets that. Then we do workup. We add a little bit of H plus, and we get our primary alcohol. Primary alcohol from the ester. So lithium aluminum hydride will add twice to an ester in order to create a primary alcohol, right? And the mechanism here is we get the addition, and then we get the reforming of the carbonyl and the loss of the leaving group, and then we get another addition. So this is what happens with esters, right? They have that leaving group there. And now that oxygen is not a great leaving group, but think about the difference between the intermediate before it and the intermediate after, right? So if we look at what happens here, we go from this negatively charged intermediate that only has single bonds, right, to a neutral aldehyde and a negatively charged oxygen over here. And so if we think about between these two steps, which side of this reaction is more stable, right? There's not a lot to choose from between them. They both have negative charge on an oxygen, right? This one has a pi bond in place of a sigma bond, but notice that what happens as soon as we make that pi bond, so we might say that this equilibrium is pretty even, right? There's not one side that's favored over the other, but what happens when we get to this side is our lithium aluminum hydride comes around, adds H minus, and all of a sudden we're down here and then we're stuck. We can't go backwards from here. We can't have this regenerate H- and remake the aldehyde. And so this equilibrium kind of bounces back and forth between these two until that aldehyde reacts with the H-, and then slowly everything kind of filters down until we get all the primary alcohol out of this reaction, right? So these two things are probably in about equilibrium because each of them has a negative oxygen on it. We have about the same number of bonds, right? We have one neutral compound here. We have one negatively charged compound on each side. And so that equilibrium doesn't really favor one side or the other, but both things are present. And so as soon as we react that H- and get rid of that aldehyde, the equilibrium reestablishes itself. It makes more of the aldehyde, and the lithium aluminum hydride reduces the aldehyde. Then it makes more of the aldehyde, and the lithium aluminum hydride reacts again and again and again and again, and it keeps going, right? And so the nice thing about this process is that eventually everything filters down to the same place. Everything goes to the primary alcohol from the ester. Okay, so what would happen if we did a Grignard reagent with an ester? So let's use the same ester just because, well, let's use a different ester because that way we'll see that the esters can be whatever. We'll use methyl benzoate. And I'm going to use, let's just do ethyl Grignard. Okay, so take a moment and kind of predict what you think will happen. Go back and look at the lithium aluminum hydride reaction and see if you can use that to kind of, we know how esters in general react now, especially when they're in the presence of good nucleophiles like this one. Right? And so we have a good nucleophile here. That good nucleophile is going to attack that carbonyl carbon. We're going to break the carbon-oxygen pi bond. We're going to make a lone pair on the oxygen, and we're going to get to an intermediate that will look very familiar. And we got 2 carbons there, right? So we had 2 carbons in our starting material. Those 2 carbons, so this carbon here is this carbon here. We use that carbon-magnesium pair of electrons to add and make this new bond here. So we have 2 additional carbons added to the structure. But now this intermediate, again, we have this negative oxygen here, and we have something that's kind of a leaving group here. And so what we can do is we can have this negative charge form the carbonyl and kick out that leaving group, right? And so it's kind of an elimination reaction almost. We're making a pi bond and losing a leaving group. So if you think back to last semester, you can draw that connection. And once again, we have an equilibrium that's kind of evenly distributed. We have negative oxygen over here, we have negative oxygen over here. The magnesium bromine is probably hanging out with this oxygen here just to make things. So far so good. We can make a ketone out of an ester. What happens if we have the magnesium bromide in excess? Right? The same thing that happens with the lithium aluminum hydride in excess, we get a Grignard reagent that's hanging around when a ketone shows up. And we know what happens with Grignard reagents and ketones, right? The Grignard adds to the ketone carbonyl carbon. We break the carbon-oxygen pi bond. We make a lone pair on the oxygen. Stop me if you've heard this one before. And what you end up with is now we've added 2 more carbons. Now we can work this up with H+, right? That replaces the, or neutralizes the negative charge, and we end up with a tertiary alcohol. Right? From an ester with 2 equivalents of the Grignard added. And so often, you kind of have to have an excess of the Grignard around because the second reaction happens so fast. If you try to do this with only 1 equivalent of Grignard, what will happen is half of the Grignard will react with the ester and the other half will react with the ketone that comes out. And so you'll have half alcohol and half ester, which isn't great, right? So instead what we do is we just add an excess of ethyl magnesium bromide. That reacts once to make the ketone, it reacts twice to make the tertiary alcohol, and we get this. So Very similar to what happened with lithium aluminum hydride, right? If we look at these two mechanisms side by side, they are exactly the same thing. The only thing that we've changed is that we've changed H minus out for a carbon nucleophile in the Grignard reaction, right? So let's look at those two right next to each other. If I can get this thing to switch slides, right? Lithium aluminum hydride, we add H minus, we kick out the leaving group, we remake the carbonyl, we add H minus again, and then we do workup with H plus. Grignard reaction, we add the Grignard, we kick out the leaving group, we remake the carbonyl, we add a second equivalent of Grignard, and then we neutralize with H plus to give ourselves the alcohols. So these kinds of nucleophiles, so nucleophiles adding to esters tend to do this kind of substitution. You add into the ester, we lose the leaving group and remake the carbonyl. Now, in the case of H minus and Grignards, when you remake the carbonyl, you make things like aldehydes and ketones, which we already know other reactions for, right? So the question is that always the case? Do we always get that reaction? Or, right, is there a different kind of thing that happens when we use other nucleophiles? So carbon nucleophiles and hydrogen nucleophiles, H minus and Grignard, tend to react like this. When we react heteroatom nucleophiles, we're going to see that we get a different kind of situation, and that will be the next video.